So are you fired up about today's lecture?
Woo-hoo-hoo.
You're more fired up about today's quiz. Alright. What is a solvolysis reaction? Well, it's a reaction where the solvent that you use to dissolve up the substrate also acts as a nucleophile. So when we think about solvents, we don't normally have hydroxide or alkoxide as solvent. We have things like water and alcohol, so that must mean a solvolysis reaction is, what do you think, SN1 or SN2? We're going to start making the distinction what's SN1 and what's SN2, whether it's unimolecular or bimolecular. It can only be bimolecular if we have a strong nucleophile. That's why you want to know the difference between strong and weak nucleophiles, so you can tell me whether it's unimolecular kinetics or bimolecular kinetics, because we'll also get to E1 and E2 eventually. So this is 2-bromo-3-methylbutane, and we're going to use water. I'm going to just put it how you might see it. Question mark. So I'm actually going to show you the mechanism. Since we know it's going to be an SN1 reaction, and we know that because water is a weak nucleophile, and we have a secondary alkyl halide, so that's allowable. And this is the rate determining step, forming the carbocations. The rate limiting step or determining step. So we want to learn what carbocations are known to do. And that's the new information today. What type of carbocation do I have here? It's a secondary carbocation. And you get to learn a new reaction arrow. Reminds me of my Hot Wheels toys, right?
What does that thing do?
This means rearrangement. So these electrons in this, holding this hydrogen, go right over there. And now I have this thing here. And what type of carbocation is this? It's a tertiary. And we learned that tertiaries are more stable than secondaries. So carbocations can rearrange. And this is a hydride shift. Remember that guy? That's hydride. It shifted from this carbon to that carbon. So if nature can do it, it's going to form a more stable carbocation. Alright, so here's the attack of the nucleophile. Oxygen likes to have 2 bonds. It's got 3. Let me not forget my bromide. It's still out and hanging around in solution somewhere. So water is amphoteric. What does amphoteric mean? It can behave as both what? Absolutely acid and a base. So now it's going to behave as a base. Grab that proton there. So this might be step number 4. So here's a hydronium ion, which can counterbalance bromide. So everything's neutral here as far as charges. Charges are neutral, but the system probably goes acidic. So a hydride shift, something brand new for us today. Rearrangements. Carbocations can rearrange to form a more stable carbocation. So this is almost identical to what I chose. 2-bromo-3-methylbutane. Little different nucleophile. An alcohol behaves quite a bit like water. And here we see a not rearranged product. And here we see the rearranged product. And there's a lot more of this in the reaction flask than this thing here. So if there's a small group on the adjacent carbon atom, you can have a hydride shift or a methyl shift. And here they draw it being a concerted thing. Now probably as fast as this leaves, this moves over and we form a tertiary carbocation and not a, this would be primary. This thing just left. So this would be concerted because nature abhors a primary carbocation. So that moves over, forms a secondary, a tertiary carbocation. So how do we predict whether it's going to be unimolecular or bimolecular. That's what the 1 and 2 mean, right? What does the S and the N mean? Right, nucleophilic substitution. So here we see the best thing for an SN2 reaction is a methyl halide, followed by primary, and then secondary. Earlier slide had a double inequality saying doesn't happen with tertiary. But we make this prediction by knowing whether it's a strong nucleophile or not. If it's a weak nucleophile, it does unimolecular nucleophilic substitution. And many times the nucleophile may also be used as the solvent. That's what we call a solvolysis reactant. What solvents are good for SN1 reactions? Polar protic solvents. The polar is just a given. We probably need things polar enough to dissolve up our substrate. Polar, aprotic. What?
Protic are the acidic ones, right?
Protic are the acidic ones. So here we want polar aprotic because the acidic proton normally protonates the nucleophile. Alright, so here is bimolecular kinetics. Alkyl halide and nucleophile have to collide together. Concerted thing happens. Nucleophile forms a bond. The halide leaves. Here the alkyl halide just gives up the leaving group. SN2 we have inversion at a chiral carbon. Here, since we form a carbocation and the nucleophile can hit from either side, we get racemization. Here there's no carbocation rearrangements, and here there are carbocation rearrangements. So this last slide puts it all together. The previous slide was much more concise. This is repeating all the same things, has some added features. SN1, weak nucleophiles. SN2, strong nucleophiles. What kind of substrates are best? Leaving group, same. We both want good ones. We don't want fluoride for a leaving group. We don't want hydroxide as a leaving group. Silver nitrate is used to force an SN1 reaction on a substrate that's not good for one. First order kinetics, second order kinetics, rearrangements are common. SN2, impossible. Any questions? That concludes chapter